So in CH activation, we need to have the activator. The name itself, they're displaying its character means its activator means it activates the catalyst by scavenging the halide from that corresponding transition metal complexes. And the silver hexafluoroantimonate is the most commonly used as an activator in the field of CH activation. So additives have also a crucial role for in the field of CH activation, and additives are divided generally in three types, that is acetate additives, acid additives, and basic additives. Mostly used acetate additives are sodium acetate and silver acetate. The acetate are playing a crucial role while formation of CH activated product, and acid additives are used for quenching the metal cycle, that is we call proto demethylation, and sometimes we need the basic additives, and carbonate salts are most common basic additives. So if reaction is oxidative process, then we need to have the oxidant to regenerate the metal catalyst at the end of the reaction. And mostly used the copper acetate is the common oxidant, copper salt, and silver based oxidants are silver acetate and silver carbonates are used. Apart from this, solvents are also playing a role, but most of the solvents, that is dichloroethane and THF, are used in the field of CH activation. So apart from directing group and coupling partner, we have to screen various components to reach the right cocktail. Hence, it is one of the challenging tasks in the field of CH activation. Coming to the earlier report, in 1955, Murahashi and co-workers has reported the first CH activation reaction, where they have done the carbonylation of the corresponding imine as well as the diazobenzene directing group by using cobalt as a catalyst. But unfortunately, they are unable to isolate the CH metal, metal cobalt cycle. Hence, the CH activation was still unproved in this step. Later in 1963, Clayman and Debug has isolated the nickel cycle by employing nickel catalyst with diazobenzene as a directing group, and they isolated the purple blue color organonickel species. And this nickel species further transferred into the corresponding product, deuterated product, by using deuterated lithium aluminum hydride. But Murai and group has used first time ruthenium as a catalyst for the CH activation, and they have developed the alkylation of the acetophenone by using alkene as a coupling partner, where carbonyl is acting as a directing group. In fact, this is the first report on the ruthenium catalyst, and after this report, we can say that the era of CH activation has started, because various groups has jumped into the CH activation reaction, and they started by using ruthenium catalyst. But the journey of rhodium has started in 1994, when Lim group has reported the alkylation by using pyridine as a directing group, and they employed rhodium 1 catalyst. This catalyst, we can say that Wilkinson catalyst. Then various group has started by using rhodium 1 catalyst, but high valence rhodium catalyst called as rhodium 6 star Cl2 dimer used first time Mura and all in 2007. They have developed the annulation reaction of benzoic acid with the acrylate as well as alkyne as a coupling partner. After this report, various group has used different kind of coupling partners. For example, simple alkene, styrene, acrylate, allene, as well as the allyl acetate, allyl carbonate, or allyl halides as a coupling partner to achieve the CH activation product at the ortho position by using different directing group under rhodium catalyst. Apart from this directing group, one of the heterocyclic directing group named as melimide, which is very important in the field of medicinal chemistry as well as in pharmaceutical chemistry. It contains the highly electrophilic double bond. We can say that it is highly activated double bond. And one of the great advantage of this melimide is we can convert this melimide to the corresponding gamma lactam pyrrolidine derivative. This gamma lactam and pyrrolidine are found in various natural products. So in the field of CH activation, Falk group has employed maleimide as a coupling partner by using benzamide as a directing group by using rhodium, and they achieved the 4+1 annulation of the benzamide with maleimide. But in case of maleimide, the Heck type product was not explored until 2018. So we have first time reported the Heck type product of maleimide with the acetophenone, where ketone is acting as a directing group by using rhodium catalyst. So in case of maleimide, getting Heck type product is difficult, and how it is difficult, I will explain in further slides. So by inspiring this work, we thought to couple maleimide at the superposition of indole, because indoles are found in various natural products and in different drug molecules. And if we look at the structure of the indole, due to presence of the spiral type ring, the electron density will be more at C3 position and then C2 position. Hence, to achieve the C4 and C7 substituted derivative, it is very challenging task when C3 and C2 positions are unblocked. So C4 and C7 substituted indole derivatives are found in various natural as well as in various drug molecules. So previously from our group, first time we have reported the C4 alkylation by using acrylate as a coupling partner, or different activated coupling partner by using aldehyde as a directing group under ruthenium catalyst. Later, again we have shown that the electronic nature of directing group by achieving the C4 as well as C2 alkylation of the indole directing group by using indole derivative by using carbonyl directing group, where COCF3 is giving the C4 alkylated product, and where acetyl group is responsible for the C2 alkylation reaction. Meanwhile, various groups have used the directing group on the nitrogen atom, and they couple the nitrogen at the C2 position of indole, and all these reports are hydroarylated by using different transition metal catalysts. I would like to withdraw your attention here that in case of acyclic coupling partner, for example, acrylate, acrylic acid, etc., the formation of Heck type product is very easy. While in case of maleimide, as I told earlier, that getting Heck type product in case of maleimide is not easy, because if you look at this intermediate, which is formed by the insertion of maleimide between Rhoda cycle, the beta hydrogen is anti-periplanar with respect to this rhodium. So due to lack of syn periplanar, it cannot undergo the beta hydride elimination, and this bond we can't rotate because of the restricted rotation due to this small ring. So what we thought, by using base which can abstract this beta proton with respect to rhodium, and that can promote the simple E2 type elimination, so that we can get the Heck type product in case of maleimide. So with this idea, what we thought, by using this base condition and the CH activation condition, we can couple maleimide at superposition of indole by using COCF3 as a directing group, and on the other hand, by using acid, we can quench this metallocycle so that we can get the hydroarylated product. So just we thought, just changing the switching the additives, we will get the two kind of different products. So with this idea, we started our optimization reaction with the indole COCF3 as a directing group with maleimide under rhodium catalyst, and then we are screening the various oxidant additives and different solvents. Finally, we got the 70% hydroarylated product when we use the silver acetate and acetic acid as a additive. Importantly, while changing the additives from acidic to the basic, called as silver carbonate, we got the 75% Heck type product at superposition of indole. So in short, just switching the additives, we are going to get the two different products. So, and with the optimization condition in hand, we went further for the substrate co for 1,4 addition product, and various substituted indole derivatives are working well under 1,4 addition product, 1,4 addition condition, and yield was moderate to good. Not only 1,4 addition, the different kind of Heck product is also forming for various substituted indole derivative under CH activation condition. Different Malimide, for example, N-phenyl, N-benzyl, N-cyclohexyl, most importantly, plain malimide, means free NH also working, and yield was moderate to good. After finishing the substrate cope, we went further for the some control experiment which helps the design the mechanism. So in first reaction, instead of malimide, we used the deuterium as a coupling partner, and we observed that the deuterium was incorporated at the C2 and C4 position of indole by 66%. So this reaction is indicating that the CH activation step may be a reversible step. And in second reaction, instead of acetic acid, we have employed deuterated acetic acid. And in that, we observed that the formation of this deuterated product by 13% and 11% on the malimide ring. So this reaction is showing that the acetic acid is responsible for the quenching this metallocycle, that is we called as the proto demethylation. Then we thought to know that whether our hypothesis is correct, or this hydrorelated product is undergoing the formation of HEC type product under CH activation condition. To check these things, we employed this hydrorelated product under the HEC type condition. So there was no reaction. So that means this HEC product is not coming from this hydrorelated product. So based on this control experiment and previous literature precedents, the tentative mechanism is shown here. Firstly, this rhodium CP star catalyst will undergo the formation of active catalyst, which is called rhodium active catalyst, which is called A, which will undergo the formation of CH activation product, that is called Rhoda cycle, denoted by B. And this Rhoda cycle coupled with malimide, and malimide will insert and form the intermediate C. The intermediate C, in presence of acid, as I told, acid will quench this this intermediate, and that is called proto-demethylation, and we will get the 1,4 hydrorelated product. While in presence of base called as Azo2CO3, it will promote the E2 type elimination, and we will get the HEC type product at C4 position of indole. So in summary, we have developed the rhodium catalyzed switchable oxidative HEC type as well as 1,4 addition product at the C4 position of indole by using COCF3 as a directing group. The most important is additive is playing for switching the product. So after coupling malimide at the heteroarene called as indole, again we thought to couple the arene at double bond of the malimide, because 3 arylated malimide derivatives are present in various natural products, and there are some derivatives are biologically active molecules. That's why they have importance in the field of medicinal as well as in pharmaceutical chemistry. Some example I shown here, which can act as antimicrobial, anticonvulsant, and inhibitor of monoglyceride lipase, etc. Coming to the previous literature, we found that in 1955, Vogel group has done the Mirwin reaction of malimide by using copper, and they achieved the arylation at the double bond of the malimide. After a long time, Capretta has done the Suzuki coupling reaction of bromomalimide with boronic acid to achieve the arylated product at double bond of the malimide. Recently, Zhou group has reported the HEC type coupling between the aryl iodide with the malimide by using palladium to achieve the 3 arylated malimide. So one thing is that in all these reactions, we need the pre-functionalized starting material, and after the reaction, there is wastage of halogen atoms. In CH activation route, previously we have reported the decarboxylative 1,4 addition of the arene nucleophile to the double bond of the malimide by using rhodium catalyst, where acid is acting as a directing group. Later, Professor Mahiuddin Vaidya from IIT Madras has reported similar transformation by using ruthenium catalyst. So in both of these report, the HEC type product of malimide, means decarboxylated HEC type product, was not formed. The reason, as I told earlier, because the lack of syn periplanar beta hydrogen with respect to this rhodium, that's why it cannot go the formation of HEC type product. And previously, as I told you, we have reported the first HEC type reaction of malimide with the acetophenone under rhodium and under basic conditions. So by inspiring this work, what we thought, we can couple we can couple benzoic acid at the double bond of the maleimide under basic condition, so we can get the Heck type product. So we can call this is intermediate, because at high temperature this acid group can undergo the decarboxylation, so that we can get the direct decarboxylative product, that is 3-arylated maleimide. While just lowering the temperature, we can get the 1,4 addition product, that is Spiro compound. So with this idea, we started our reaction with benzoic acid, entry first, the benzoic acid with the copper acetate in the THF solvent, but unfortunately, we did not get the any product. Hence, we increased the nucleophilicity of the directing group by, instead of using acid, we use the sodium salt of benzoic acid, and surprisingly, we got the Heck type product in 60%. Then the screening various salt, oxidant and solvent, finally we got the 79% of isolated yield of Heck type product when we use the THF solvent and lithium salt of benzoic acid by using copper acetate as an oxidant. While just switching the solvent from THF to TFE, we got the 67% of the 4+1 annulation product. So in short, just switching the solvent and the salt of benzoic acid, we are going to get the two different products. So with the optimized condition in hand, we went further for the substrate cope of decarboxylated Heck type product, where the different kind of maleimide derivative and benzoic acid salt derivatives are working well, and yield was moderate to good. But important thing is that the N-benzyl maleimide derivative and N-phenyl maleimide derivatives are acting as a antimicrobial and inhibitor of monoglyceride lipase respectively. So in short, in one pot reaction, we are synthesizing these two natural products. So different sodium salt of benzoic acids are also working well under the 4+1 annulation condition. Some few examples I shown here, and yield was moderate to good. After the substrate cope, we have done the scale up experiment where the 8 millimole scale, we got the 56% of the Heck type product as well as 4+1 annulation product in 39%. After scale up reaction, we have done the deuterium incorporation reaction, where instead of maleimide, we use the D2O as a coupling partner. In that case, we found that the deuterium incorporated at the ortho position of this acid derivative. So this reaction showing that the CH activation step may be reversible. So based on this control experiment and previous literature precedents, the mechanism I shown here, and this mechanism is similar as I shown in previous chapter. In first step, rhodium will undergo the formation of the active catalyst A, which will undergo the formation of the Rhoda cycle by CH activation, and this will coordinate with maleimide and form the intermediate C. This intermediate C on the E2 type elimination will form this Heck type intermediate. More importantly, this Heck type intermediate D in presence of THF solvent will undergo the decarboxylation and forms the Heck type product. While switching the solvent from THF to TFE, it will undergo the 1,4 addition product, that is 4+1 annulation product. So in summary, we have developed the rhodium catalyzed CH activation, that is switchable decarboxylated Heck type as well as 4+1 annulation reaction with maleimide, and the solvents are playing crucial role in switching the selectivity. So after exploring the maleimide as a coupling partner in the field of CH activation, we thought to couple the non-activated olefinic coupling partner. One of the non-activated olefinic coupling partner is allyl alcohol, because allyl alcohol was not explored well in the field of CH activation. So we thought to couple allyl alcohol at the C4 position of indole, because as I told earlier, the C4 substituted indoles are important. They are present in various alkaloid. Some example of ergot alkaloid and haploindoles are shown here. By looking at previous literature, allyl alcohol has used first time by Glorious group. They employed the coupling of allyl alcohol at C2 position of indole derivative by using pyrimidine as a directing group, and they achieved the hydroarylated product under rhodium catalysis. While Kanai group has done the allylation at the C2 position of indole by using same directing group under cobalt catalysis, and similar transformation has done by Kapoor and Kapoor et al. In 2016, where they used the ruthenium catalyst. But in 2019, Professor Punyamurthy from IIT Guwahati, they have employed the Movata Baylis Hillman coupling partner at superposition of indole to achieve the allylated product. But in this case, apart from acetyl directing group, the other directing group, for example, aldehyde, pivalyl, and ketone directing group are ineffective under these conditions. So our hypothesis was by using carbonyl as a directing group, we can couple the allyl alcohol at the superposition of indole by using rhodium catalysis, so that we can get the hydrolylated product. And if two carbonyl are two carbonyls are there in same molecule, so it can undergo the intramolecular aldol condensation, so that we can get the tricyclic moiety, which this moiety is found in some alkaloid derivative. So with this idea, we went further for the optimization reaction with the indole 3-carboxylaldehyde as the directing group, allyl alcohol as a coupling partner by using rhodium as a catalyst, and screening various solvent, temperature, and additives. Finally, we optimized the condition where we got the 93% of isolated yield, that C4 alkylated product by using HFIP solvent, adamantane carboxylic acid as additive at 55-degree temperature. After optimization, we have shown the difference. Their indole derivatives are incorporated under CH activation conditions, and the yield was moderate to excellent. Not only aldehyde as a directing group, the acetyl as well as pivalyl group is also working as a directing group, and the yield was excellent in both of the cases. So in synthetic utility, we have done this reaction at 1 gram scale, and we got the 90% product, C4 alkylated product. After synthetic utility, the obtained product 3AA and 3AB employed under basic condition, so that we can get the aldol product, and we achieved this successfully. This tricyclic molecule, which is found in means this tricyclic skeleton is present in ergot alkaloid as well as in haploindole alkaloid. So in deuterium study, instead of allyl alcohol, we have used the deuto as a coupling partner, where we found that the deuterium is incorporated at superposition of indole by 28%. So this means the CH activation step is reversible. After this deuterium study, we have calculated the KH by KD by employing this undeuteriated indole derivative as well as deuterated derivative reaction with the allyl alcohol under standard condition, and we found that the KH by KD is 3.08. So that means the CH activation step may be the rate determining step in the catalytic cycle. So based on that control experiment and previous literature precedent, we proposed mechanism here that is similar to the previous chapter, where the rhodium will undergo the formation of active catalyst, which is responsible for the formation of CH activated Rhoda cycle, which will coordinate with allyl alcohol and form the inserted product C, and this inserted product C will undergo the beta hydride elimination and forms this intermediate D, which tautomerism on tautomerism will form the more stable hydrolylated product. So in short, we have achieved the rhodium catalyzed functionalization at superposition of indole derivative by using allyl alcohol as a coupling partner, and the obtained hydrolylated product can lead to the 3,4-fuel tricyclic indole derivatives. So after coupling allyl alcohol at the superposition of indole derivative, we thought to couple the benzamide in a such a way that so we can get the annulation product in situ. So that is turning to my last chapter. And the lactam or 7-member lactams are present in various natural products, and the 7-member nitrogen containing alkaloids are also present in various natural products. And by looking at the previous literature, the allyl alcohol was first time used by Fogno group in 2011 by using benzamide as a directing group. With actually they have used the different coupling partners, alkene coupling partner, and they have shown the allyl alcohol as one of the substrate in substrate group. Later, Jiang and group in 2013 they have employed the allyl alcohol at ortho position of benzamide as a directing group under rhodium catalysis. They use the hydrolylated product at the ortho position of this benzamide. In same report, they use the acetanilide as a directing group. In that case, they got the 3+2 annulated product. While Cui group they have synthesized the 7-member lactam by incorporating this diazo as a coupling partner by using rhodium catalyst, while Glorious has reported by using acrolein as a coupling partner under rhodium catalyst to achieve this 7-member lactam. Same year, White Oak group has reported the similar kind of transformation by using cobalt catalyst by using acrolein. So for preparation of this lactam, 7-member benzolactam, people are used the acrolein, which is unstable, and acrolein will undergo suddenly polymerization, and that is readily unavailable also, especially in India. But allyl alcohol is bench stable, which is chemically equivalent to alpha beta unsaturated ketone. So we thought that we can do in situ generation of acrolein from allyl alcohol, so that in situ generated acrolein can couple with this benzamide and forms the 7-member benzolactam product by using rhodium. So with this idea, we started our optimization reaction with the benzamide as a directing group with allyl alcohol under rhodium catalysis, and screening various conditions. Finally, we achieved the 73% of isolated yield of this benzolactam at 60-degree temperature by using copper acetate as an oxidant and by using HFIP as a solvent. After optimization reaction, we started substrate cope for benzamide derivatives, where different substituted benzamide derivatives are working well under CH activation condition. But more importantly, when we use the N-phenylbenzamide as a directing group, we found that there is no formation of benzolactam product, and there was 20% of the hydrolylated product was there. So this reaction was at 24 hours. So the same reaction we repeated at 48 hours. So we found that the formation of benzolactam by 25% and 10% of this hydrolylated product. This means that this benzolactam is forming via this hydrolylated intermediate. Not only benzamide derivative, the cinnamamides are also working well under this standard condition. Various substituted cinnamamides are working, but yield is moderate to good. After substrate cope, we have done the scale-up reaction at 6 millimole scale, and we found that the formation of benzolactam by 70% yield, and in that case, near about 50% starting material benzamide we have recovered. After the obtained product, benzolactam 3AA reduced by using S2PDC, and we got the 85% of reduced the saturated benzolactam product. And 3MA, where this NH is free, this is not substituted, reduced by using S2PDC, and we got the 93% of the saturated benzolactam. This saturated benzolactam ring has importance because it is useful for the preparation of this derivative, benzolactam derivative, which is indicated by 8 and 9, and which is prepared by Masagar group in 2009. So this derivative is acting as a dopamine D3 receptor, and they can use in the treatment of neurological disorder. So we can call that schizophrenia. Apart from this, the saturated benzolactam ring can be transferred into the corresponding this chiral alkaloid, which falls under cephalotoxus alkaloid, and these things are achieved by the Meyers et al. In 1993. So in deuterium study, instead of allyl alcohol, we have used the deuterium as a coupling partner. In that case, we found that the formation of the deuterium at ortho position of benzamide by 25%. So again, we can say that the CH activation step may be the reversible step. And next, we calculated the KH by KD by, as I told earlier, that undeuteriated benzamide and deuterated benzamide has employed parallelly with the allyl alcohol under optimal conditions. So we found that the value of KH by KD was 3.1. So that means the CH activation step may be the rate determining step in the catalytic cycle. So as I told, our hypothesis was to convert the allyl alcohol to the its corresponding aldehyde in situ. To check these things, we have done some control experiment. So we use the crotyl alcohol treated with under optimal condition, and we found that the formation of crotonaldehyde by 32%. So this means that the crotyl alcohol means allyl alcohol is undergoing the formation of the acrolein in situ. So the same reaction we have repeated in the absence of rhodium. So we found that there is no formation of this corresponding crotonaldehyde. That means the rhodium is responsible for the formation of this allyl alcohol to the corresponding aldehyde. So again, one reaction we have repeated in the absence of copper, but in presence of rhodium. In that case also, we did not get any kind of this corresponding aldehyde. So here we can say that from these three controls, alcohol is undergoing the formation of the alpha beta unsaturated carbonyl compound, and where the rhodium catalyst is acting as an oxidant and copper is acting as a co-oxidant, which is helping to regenerate the rhodium catalyst. Apart from this, we have employed the acrolein in place of allyl alcohol. In that case also, we got the 70% yield. When we use the crotonaldehyde, we got the 50% of this benzolactam product. So from these all controls, we can say that rhodium catalyst has a dual role. That is one for oxidation of alcohol to the corresponding aldehyde, and second one for the CH activation step. As in substrate COP, I told that when we use the N-phenyl benzamide, we got this hydroarylated product. So we prepared in large scale and we used for some control experiment. When this hydroarylated product we employed under again the standard condition, we got the formation of this benzolactam, an annulated product by 22%. So that means again we can say that this benzolactam is forming through this intermediate. Then we have repeated this reaction in the absence of all reagent. Only we treated in HFIP only, so we found that there is no reaction. So that means some reagent is responsible for the formation of the cyclized product. Then we have done various control where we found that the adamantane carbonic acid is the adamantane carbonic acid, rhodium, copper acetate, and copper acetate with acid. These are not responsible for this cyclization. When we use the silver hexafluoroantimonate in HFIP, we found that the formation of 33% of this annulation product. That means silver salt has also dual role in this reaction. The first one is halide scavenger to scavenge this chlorine from this catalyst, and second one to act as a Lewis acid for this annulation product. So based on previous literature precedents and our control experiment, the proposed mechanism is shown here, where in first step this active catalyst rhodium is formed from this rhodium CP*Cl2 dimer, and this active catalyst undergo the oxidation of this allyl alcohol and forms the rhodium 1. That rhodium 1 will regenerate by using copper as a co-oxidant. And another one thing, this active catalyst rhodium is also undergoing CH activation and forms the rhodocycle B. This rhodocycle B coordinate with the acrolein, which is formed in situ from allyl alcohol and forms the CH activated product, which is denoted by C. And this C will undergo the proto-demethylation and forms the hydroarylated product, and this is isolable when R is equal to phenyl. And this hydroarylated product under presence of silver salt undergo the formation of this cyclized product. Even though we have shown that the allyl alcohol can oxidize in situ to the aldehyde, we cannot neglect that the allyl alcohol can also direct couple to this rhodocycle and form the CH activated product, and then it will undergo the beta hydride elimination and form the hydroarylated product. So in summary, we have developed the 4+3 annulation of primary, secondary, and cinnamomate derivative by using allyl alcohol as a coupling partner. And in this reaction, the rhodium is playing a dual role that act as oxidant as well as catalyst for CH activation. Silver acid hexafluoroantimonate also playing dual role, that is Lewis acid as well as for the halide scavenger. The obtained product, one of the obtained product can act as a dopamine 3P receptor. So in summary, we have shown the coupling patterns of maleimide at C4 position of indole as well as octo position of benzoic acid in section A. While in section B, we have shown the coupling patterns of allyl alcohol at superposition of indole and ortho position of benzamide as a directing group under rhodium catalysis. So in academic, I would like thanks to my research supervisor, Professor K.R. Prabhu, who helped me in my good and bad time for his motivation and most importantly his freedom to work in lab. And he is a good teacher also. I like the way of his teaching. So thank you to my research supervisor, K.R. Prabhu sir. I would like to thank Professor K.R. Prasad, Professor Santanu Mukherjee sir, Professor T.K. Chakravarti sir, and Professor A.T. Biju sir for allowing me to use their lab facilities and their lab chemicals. I would like thanks to Chairman of the department, faculty members of the department, and office staff of the department. I would like thanks to Murthy sir and instrumentor operators who helped me to analyze my compound by NMR in whenever I needed. I would like thanks to my colleague Rajake and Ravi Devarajavappa who helped me to finish the couple of projects. My senior, I would like thanks to Dr. Kiran Bettadapur, Dr. Muniraj and Dr. Vinayak for their helpful suggestions during my PhD time. I would like thanks to all my lab seniors and project lab mates, that is Manna, Avan, Anil and Sudarshan. I would like thanks to all my batchmates, and especially I would like thanks to my past teachers, the Coach sir, Shinde sir and Parit sir. I would like thanks to my parents and all my friends. I would like thanks to Department of Organic Chemistry and Indian Institute of Science for their infrastructure, facilities, and for the fellowship. And I would like thanks to the examiner, Professor Ramesh, for reviewing my thesis and for conducting my thesis defense. I would like thanks to Professor S. Chandrasekharan for inviting for accepting my invitations. So thank you all for your kind patience.
Thank you, Mahadev. Thank you, Mahadev. And Professor Ramesh, it is open for questions and queries, and examination is starting now.
Okay. First of all, thanks, Professor Prabhu, for giving me the opportunity to go through the thesis. I really enjoyed the work. And Mahadev, good presentation.
Thank you, sir.
Okay, I really enjoyed going through your thesis. Well written. I really appreciate, especially the introduction part. You have written very exhaustively, so that you know what is lacking in the literature, so that you can continue on the work. Very good introductory work. Good presentation of your thesis and good presentation of your work in today's lecture also. Very nice. Okay. Good work.
Thank you, sir.
I have a few questions. Can you go to the slide number 13, 1-3?
Yes.
So, okay. You said that this fourth position and seventh position, okay, crucial for accessing how to functionalize unblocked C3 and C2 position. Okay, that means you cannot activate the fourth position if you have an unblocked and C3 and C2 position. But that's what I understand. Am I right?
Yes, sir.
But in all your activation, you are blocking your C3 with a group, which is going to be the directing group, right? So my question
sir,
is
your voice is breaking, sir. I question did not hear.
No, but you say that in the fourth position, indole and its reactivity fourth position, I think you cannot functionalize the fourth position with unblocked C3 and C2 positions. That is what you are saying, right?
Right, sir. Right, sir.
But in all your synthesis, you are using the third position with a directing group. You have already blocked the third position with a directing group, which is acting as a directing group, right?
Yes,
so that means in your case also it is a kind of a blocked position at the C3 to activate the C4. Am I right?
Yes, sir.
Okay. Now you say that generally electron-rich group is used as an activating group, which is a very well valid point. That is a general statement you made. But if you go to the next slide where you are doing actual reaction, not your reaction, where you are using a COCF3, right? You are using a trifluoroacetyl group as the directing group in your reaction, right?
Yes, yes, sir.
How good is it an electron donating group? What would happen if you have used the simple acetyl group? Because in the later part of your work, you have shown some of the work with the simple acetyl, COCH3. But here you have done the reaction with the trifluoroacetyl group, right? So,
yes, sir.
Does it work only with the trifluoroacetyl group, or will it also work with the simple acetyl group?
Actually, in presence of acetyl group COCS3, it can direct at C2 position as well as C4 position. But in case of COCF3, it will direct only C4 position, because the COCF3 group is highly electron withdrawing group. So it will decrease the electron density on C2 position. So when COCF3 is present, so in comparison, C4 position having the more electron density. So that's why when COCF3 is present, the metal cycle is going to form at this position.
So
While
metal-
acetyl group is, yes sir.
Yeah, okay.
While acetyl group is not that much electron withdrawing as compared to COCF3, that's why electron density is somewhat similar at both the case. And in case of, that's why in that case, it is forming metal cycle at both of these cases. But in COCF3, it is going for only C4.
Now the first step, when you in your reaction, when you use a metal, okay,
Yes, sir.
how do you activate this CH? What is the first step involved in this reaction? Very first step.
Actually,
How is this proton getting removed?
yes, sir. I will show you.
Yeah.
So actually, CH activation step is either going through this sigma bond metathesis or concerted metal deprotonation. So the acetate or any basic ligand on this metal will abstract this proton. So in this case, we can call it as acetate assisted CH bond activation.
Okay.
And then yes, sir. And then CH.
Which means it is not the removal of the proton directly, first the metal center coordinates with the carbon, which is more electron rich. Okay. That is
Yes.
what.
Yes.
Okay.
Yes.
And quite often you are used in the beginning what is called an oxidative head coupling, right?
Yes, sir.
I use the term oxidative head coupling. What do you mean by oxidative head coupling?
So actually, oxidative means the product and the starting material going to lose the hydrogen. So what we call that, the removal of hydrogen, we call that the oxidation. And another one thing, at the end of the reaction, metal is also going for reduction. Means that metal is doing the oxidation of both of this starting material and reagent, removing the hydrogen overall. So that's why it is called oxidative process.
No, okay. So which means that in a simple head coupling, you need to have an halide or triflate, which you do not have in this case. That is what you want.
Yes. Yes.
Okay, good answer. Okay, just I wanted to know whether you know what do you mean by oxidative head coupling. See, in the place of this maleimide in this slide, if you use a simple cyclopentenone, will the reaction go?
Yes, sir. With cyclopentanone, reaction can go, but I have not tried. That is one thing. It can go, no problem.
Because can you go to the slide where you are using both acid and base and you are getting one product with a double bond retained and one reduced double bond? You are shown in one particular slide, probably, I'm not probably slide 22 or something like that.
Okay. Huh.
No, in one, okay, fine. This is also fine. Okay. See, in the presence of acid, we can understand that it gets the hydrolysis of the palladium, you get the hydrogen. Okay.
Yes.
And on the left hand side, do you really need a base for this reaction? You explain certain reasons for that. Can you go to the slide where you explain the mechanism saying that for a beta hydride elimination, you need the metal and the hydrogen syn to each other.
Yes.
That is
Yes,
why
sir.
it is not undergoing. Yes. So suppose if I take a simple cyclopentenone, okay, the Heck reaction will also go. In that case also, the carbon-carbon bond and carbon-metal bond will be syn to each other. There will not be an hydrogen anti to syn to the metal. But what will happen in this case? The compound C you are showing in the slide.
Yes, sir.
Okay, it is alpha to the carbon. So there will always be an equilibrium between this carbon metal versus an enolate oxygen metal. Okay.
Yes, sir.
And when the enolate oxygen metal comes back to the carbon, then it can come from two sides. One side will have the hydrogen syn to it, and one side
Yes.
with the hydrogen anti to it. The moment hydrogen is syn to it, it will undergo the beta hydride elimination. So my question is that the beta hydride elimination is also possible even in the absence of a base. Probably the rate of the reaction may be slow. So did you try reaction in the absence of a base?
Of course, sir. When we tried in the absence of acid as well as base, in that
I'm
case
not
we
saying
did not get
acid.
any kind of.
Acid case is very clear. That is clear.
Yes,
but
sir.
get the double bond, you have used a base, trying to do an E2 type of an elimination, basically.
Yes.
Right?
Actually, we tried in the absence of base, and we did not get any kind of product. So that's why we thought this base is acting means accepting the that proton, and it is going to E2 elimination. But whatever you told, that is also absolutely correct, sir. But based on our control experiment, we told that maybe E2 elimination is happening.
Okay. No. This may make the reaction go faster, but that may be a slower process because the enolate oxygen metal bond versus the carbon metal bond equilibrium should come back.
Yes.
And it may be a slow process. I just wanted to know whether you have made absence of it. Okay. Can you go to slide 31?
Sir.
Yeah. See, in this case, in the earlier cases, you have shown that the CH functionalization is taking place alpha to the carboxylic acid.
Yes.
Okay? But in this case, since you are using the temperature at 120 degrees, okay, right?
Yes, sir.
Have you proven in this case also the functionalization is happening at the alpha carbon? In 3A, have you, because in some other example you have shown that it is happening at the alpha carbon, but in this particular case also have you checked that it is happening at the alpha carbon, or first decarboxylation is happening because the temperature is so high, 120 degrees centigrade? Okay.
Yeah.
So my question whether you have tried that one?
Yes, sir. Actually, I tried, sir, but I'm not remembering as of. So we tried, but the first decarboxylation is not happening, sir.
Okay.
If first decarboxylation, if it will happen first decarboxylation, then when I tried that this parachloro, I should get the parachloro product.
Okay.
So in case, yes.
Okay. Now it's very clear. Okay. Yeah. Can you go to slide 35?
35.
35.
Yes, sir. Yes, sir.
This is not the one, probably the next one, where you are showing the mechanism. Yeah, okay.
Yes.
See, here when you are discussing the mechanism, you discussed that in DHF it is undergoing the decarboxylation, and in the trifluoroethane, right? What is that?
Yes, trifluoroethane. So yes, sir.
Ethanol, right?
Yes, sir.
It is
Yeah,
sir. But you did not discuss, see, until the structure D, okay?
Yes, sir.
You are having the structure D with the orthofunctionalization, very good, but you did not tell what is the role of the metal in directing this reaction. Is it only the solvent playing the role, or the metal also plays a role? Because with lithium you have used one solvent, with the sodium you have used one another. With lithium you have used THF, and with the sodium you used the trifluoroethanol, right?
Yes, sir. Yes, sir.
So did you try to swap the solvent? And I would like to know what is the role of the metal here, because any of D is going to be the same whether it is lithium or sodium.
Actually, thing is that, sir, When I use the lithium, the O lithium bond is more covalent, sir. So as compared to O Na bond, oxygen sodium bond as compared to oxygen lithium bond is more covalent. And when I use the lithium salt and THF, that is non-polar, so the solulysis will not mean there is not a much solulysis of this intermediate. So
My
hence,
question is, did you try this reaction with lithium in TFE?
yes, sir, I tried, sir.
So
Both
what is the result?
I got less yield, sir. 4+1 annihilation, I got very less yield, sir.
So, and what about the sodium with in THF?
In that case also I got product, sir, but yield was low. Both sodium salt means both salt are working in both conditions. But thing is that lithium salt is giving more product, decarboxyl. Sodium is giving more product, this annihilation.
So what is the reason for that? How does the solvent affect this change in the course of the reaction?
That. So when THF is present, so this THF is non-polar as compared to TFE. So this salt will not get solulysis much, and at high degree temperature, so due to low solulysis, this will undergo the decarboxylation. Means there is less polarization of this salt in presence of non-polar THF. So when we switch the THF to TFE, TFE is more polar, and this bond means this salt will get more polarized, that is called more solulysis. So due to more solulysis, this oxygen will attack on this double bond. So
you are saying it is a solvent effect in
most
on the
major
solubility,
role is solvent.
on the solubility.
Yes.
Okay. And in the next chapter where you have used aldehyde as your directing group, right? The reaction works very well with a hexafluoroisopropanol, right? As compared to any other solvent. Right? The last one and the 14, entry 14. Only with the hexafluoroisopropanol, you are getting the best yield, and it's a very high as compared to any other solvent, right?
Yes.
Any reason for that?
Yes, sir. Actually, HFIP will form the hydrogen bond more, and it is more polar also. So maybe this polarity is playing role for this coupling of aldehyde. Sorry, coupling of this allyl alcohol.
So, but instead of hexafluoroisopropanol, did you try with simple isopropanol or something like that?
Yes, sir. Isopropanol I tried, but isopropanol is not working. But trifluoroethanol is also giving 52%. So polarity is playing role here, sir. Simple ethanol, methanol, and isopropanol are not giving any kind of product. All three has not given product. I remember well. Only TFE means highly polarized solvent is only giving yield, sir.
And you have done a very interesting experiment to find out the rate determining step by doing the kinetic isotopic effect.
Yes, sir.
And that slide where you are talking about the kinetic isotopic effect, KHI.
Yes.
First of all, the K is not a capital K. Okay, it should be a small K. You are talking about the rate constant, not the equilibrium constant, right? So the KHK should be small. Okay. Second thing is that normally, if the rate determining step does not involve the cleavage of the CH bond, then the KH by KD will be approximately 1, right? And in a very ideal case where the rate determining step does involve the cleavage of the CH bond, okay, then it will be of the order of 6 or 7. Normally people say it is 7, KH by KD is 7. And now I see this is somewhere in between, okay. So can you confirmly say that the rate determining step is the one where the CH bond cleavage is happening?
Actually, the rate determining step is calculated by doing reaction at time intervals. That is the correct method. So after 15 minutes, 30 minutes, by plotting time to yield, so by that method we can determine the correct rate determining step. So this is not 100% true, sir. Actually, for this is suggested by reviewers actually. So they told to just do this one and try to know that whether it is a rate determining step or not. So that's why we done. But this is not 100% accurate.
Because it's somewhere in between the two extremes, I think.
Yes, sir. Yes, sir. Yes.
And one last question. You are using, you have very clearly explained in the last slide between the use of rhodium, silver, salt, and copper. Okay,
Yes.
copper
Yes.
oxidize. Okay, and you have also mentioned the reaction can go with a simple allyl alcohol. You don't have to oxidize to the acrolein also. But when you are using the silver salt, I could see you are always using an antimony hexafluoro compound, like a silver antimony hexafluoro. Can the simple silver chloride, silver iodide, or something like that will work in this reaction? Why do you need to have a silver antimony hexafluoride?
Actually, we can, I don't know by using AgCl or AgI will work for this or not. But what we thought, sir, silver is already present in reaction and we need AgSbF6 to activate this catalyst. So other silver salt can also activate this catalyst, but silver AgSbF6 will activate more. So what I thought, silver salt is already present in the reaction, so no need to add extra salt because yield is already 73%. So that's why I did not add extra silver salt. So.
So nice, I have done with all my questions. So what is your plan? You have done a lot of work, nice, interesting work. In fact, I would have been happy to see that since you have made this compound, you have shown that this can be used for the synthesis of the dopamine analog, dopamine receptor ligand. You could have tried one reaction and you would have got this compound by yourself. And you will get more satisfaction. Yes, you have developed a methodology, very simple methodology. And this should be a very simple reaction to couple that piperazine derivative, substituted piperazine derivative over that, right?
Actually, my professor same thing suggested that time. So we thought to do, but what happened, sir? Professor Punyamurthy reported one reaction during preparation of this manuscript, sir. So that's why we submitted as such that time.
You will have a lot of competition within India and abroad, right? For this.
Yes.
No, that's okay. No, at least for your satisfaction, after the publication is over, you could have done. So you could be proud that I have done some molecule which have some pharmaceutical interest.
Yes.
So nice work, Mahadev. I enjoyed reading. Congratulations, and defended very well your thesis. You were able to understand the chemistry what you have done, and you were able to give satisfactory answers to all my questions. Okay.
Thank you, sir.
Congratulations. Okay. Professor Prabhu, I am done.
You, sir.
Yeah, thanks, Professor Ramesh, for very nice examination, exploring a lot of things, and he also, I think I will ask Mahadeva to complete that synthesis if he is available for next 2-3 weeks. Now I request.
For self-satisfaction only.
Just correct.
I have also made a biologically important molecule.
Perfect. Yeah. So I think floor is open for the faculty members and rest of the audience for the questions and queries. Okay, Biju has a question. Yeah, go ahead, Biju.
Yeah. Hi, Mahadev. Very nice work.
Yes, sir.
Congratulations. So I have a question from one of your slides. Can you please go to slide number 47?
Yes, sir.
Yeah. So can you please explain why the deuterium incorporation is only 28% at the C4 position and why there is no deuterium incorporation at the C2 position?
Actually, sir, maybe metal cycle formation of metal cycle is very slow at C4 position maybe. So that means the number of molecules of metal cycle may be low. That and another one thing, sir, No, sir. This much I can answer.
Hello.
Mahadev?
Yes. Yes, sir.
Yeah, sorry, I cannot hear you in between.
Uh, Actually, what I'm saying, sir, the metal cycle itself is not farming in more amount, maybe. So it is farming less amount. That's why the maybe metal cycle is farming 28%, not 100%. So after formation of metal cycle, it is going back. It is reversible. By going back, it is taking the uh, deuterium of the deutero.
Okay. So do you think any role of HFIP in that? Because it can also exchange the deuterium from D2O, right?
Yes, sir. You are absolutely right. The HFIP hydrogen means OH is highly acidic. Yeah,
Yeah.
you are right, sir.
Yeah. And for the C2, no deuterium incorporation is because of the electrophilicity of the aldehyde group, maybe, right?
Yes, sir. Yes, sir.
Okay. Okay. Yeah. Thank you, Mahadev. Congratulations to you.
Thank you, sir.
Durga, you have questions?
Yeah. Thank you, Professor Prabhu. Mahadev, very nice presentation and congratulations.
Thank you, sir.
So I have first of all a confusion on slide number 37. Can you go back to slide number 30? Yeah. So here intermediate C and D, and you put acetic acid, but acetic acid is a protonation, and you should get a hydroarylated product, right?
Yes, sir.
And you should
No, sir. Actually, in this step, after abstracting proton from here, this rhodium will lose one acetate. I didn't show for clarity. One acetate will be there, OAC.
okay.
Actually, two acetates are there. One acetate will go out after CH activation,
Okay.
and one acetate is still remaining.
Okay.
After abstracting proton, that means E2 elimination will happen, and then rhodium will lose the acetate. That acetate will take the proton from our base, and acetic acid will go.
Because in some other examples, you use an external base like a silver carbonate, right?
Yes, sir.
For this reaction, but here the acetate is enough to deprotonate. And why? Why is it? Why do you need an external base in other reactions?
Actually, as far I know, the pK value of acetate means acetate is not much basic, weaker basic than carbonate. So
Yeah.
maybe it's the pK value of this hydrogen matters. Maybe acetate is not that much enough to abstract these protons.
Okay. Another question is, like you propose E2 elimination.
Yes, sir.
And have you thought about doing a kinetic isotopic experiment there by putting deuterium and to see if there is any effect on the maleimide?
On the maleimide, we have not done, sir. So
because if you go to that slide where you propose the E2 elimination and you're abstracting a proton from a maleimide, like a succinamide, not the maleimide.
Yes.
And if you already incorporated deuterium there, can you get some information whether there is a kinetic isotopic effect in that step?
Yes, sir. We can get the information, but we have not done that reaction, sir.
Okay. So the last question is, you explored very nicely the directing group effects like aldehyde and ketone. In some cases, you get a C2, especially when you have acetyl group, you get a C2 and C4.
Yes.
So, you also use other directing groups in your chemistry, such as, benzamide, acetanilide, and carboxylic acid. So have you ever tried these directing groups on indole and to see which position you will functionalize?
Yes, sir. This project.
Yeah, but most of the time you have either aldehyde or ketone, but I don't see like carboxylic acid or.
Yes, sir. Actually, in this project, we have screened the different directing group also, sir. When we screen the other directing groups, for example, I hided that slide. So here.
Okay.
So different, all other directing groups are not working under this condition.
Okay, so it's only aldehyde and ketones.
Ketones.
Not all the
CO
ketones, but only CF3 ketone. But you already explained that is because of the electronics.
Yes.
Okay. Yeah. Thank you, and once again, congratulations.
Thank you, sir.
Yeah, thank you, Durga. Raja, you have a few questions?
Hello,
Yeah,
Mahadev.
yeah.
Mahadev, first of
Hello.
all, nice talk and congratulations. So I have a
Thank you,
question. So
yes,
in all your project, you screened rhodium. What other methods you screened other than rhodium?
we screened other ruthenium, cobalt, and other rhodium also, that is already activated rhodium, that is rhodium acetate, so rhodium CP star acetate, rhodium CP star acetonitrile, like that. Some 3-4 catalysts I screened, but rhodium, those are also working, but yield is low. CP star chloride is working well.
So I have one more question. For example, if rhodium is contaminated with a palladium, it's a trace impurity. Did you try with palladium to see whether the reaction is work with a palladium or rhodium?
Actually, palladium I have not tried, sir, and I have not tried like that.
Okay. So recently, most of the scientists have seen, right, there are some trace impurities of metal, that metal can do these transformations.
Yes.
Thank you.
Yeah. Okay.
Thanks, Raja. So any other questions from anybody? If there are no more questions, we shall thank Professor Ramesh coming online for us to helping us, and I also thank Mahadev and rest of you for kind attention.
Thank you, sir.
Thank you very much, and I close this examination. I believe that Mahadeva is qualified and passed the examination. Congratulations, Mahadeva. The Professor Ramesh has already uttered that. So I congratulate Mahadeva for his work and all the association so far. And Professor Ramesh, I will communicate remaining papers with you. We shall take care. Thanks to everybody.
Congratulations, Mahadev. Congratulations.
Thank you, sir. Thank you, sir.
All the best
So,
for
yeah.
your future endeavor.
And we will sign off from this meeting. Thanks a lot. Thanks, Ramesh.
Okay, thank you. Thank you. See you.
Yeah. So I think.